List comprehensions in Python offer a powerful way to create new lists by looping and applying logic, all in a single line of code. Let's start with our matrix M, which is a list of lists. Each inner list represents a row, for example 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let's collect the second column from this matrix. When we write row of 1 for row in M, this means for each row inside M, take the element at index 1. That gives us 2, 5, 8. That is list with entries 2, 5, 8, which is the second column. So notice the original matrix stays unchanged. Next, we can also extract the diagonal items, those that share the same row and column index. So we write it as this comprehension. So this results in 1, 5, 9. List comprehensions are not limited to numbers, they work on any sequence. For example, if you write CR into static 2 for CR in spam, so this statement basically doubles each character in the string, producing this pattern like SS, double P, double A, double M. We can also apply transformations. For example, row 1 plus 1. So this statement adds 1 to each second column value, resulting in a list 3, 6, 9. And finally, we can include conditions. This means for each row in M, take the second element only if it is even. That filters out the odd values and leaves us with a list containing 2 elements like 2 and 8. So in summary, list comprehensions give you looping, filtering and transformation all in one clear expression. So they are not just concise, they often result in faster than traditional for loops. Dictionaries map unique hashable keys to values. Keys are typically strings or tuples of immutables. Use d.get iterate with for kv in item to get both keys and values. Python dictionaries can store not only simple values but also other data structures like list and even other dictionaries. So this lets us build rich and nested models that resemble real world records. For example, JSON structures commonly used in APIs. So here we have a dictionary called rec that represent a person record. The name key stores another dictionary with first and last names. The job key holds a list of strings, different job roles. The age stores a simple floating point number. When we access rec of name, we get the entire nested dictionary. We can chain indexes. So rec of name and last navigates to the name dictionary and extracts the last value. Likewise, rec of job gives us an entire job list, and rec of job and then -1 selects the last element, that is MGR. Because lists are mutable, we can expand Bob's job list directly using append function. After running rec of job dot append janitor, the updated record now includes a third job role, showing that nested mutable structures can be modified in place without recreating the whole. So this is a key difference between list and dictionaries, which are mutable, and strings and tuples, which are immutable. The nested models gives us both flexibility and structure that is perfect for representing hierarchical data like employee records, product catalogs, or JSON from an API. Tuples are like lists but immutable. They are useful for fixed collection of items and can be used as dictionary keys when their elements are hashable. A common Python pattern is unpacking, like if you write x comma y is equals to pair, which is concise and very you could say expressive. Although the tuples are immutable, they can contain mutable objects. For example, a list of 1 comma, so the inner objects can still be mutated. Now that we have explored Python objects and data structures, let's move on to how Python interacts with the outside world through files. The most fundamental function for file operation is the open function. So the open function takes 2 arguments, the file name and mode. File name is simply the name or path of the file that you want to work with, and mode tells the Python what kind of operation you want to perform. So let's break down the different modes that are available in Python. So R stands for read mode, so it is the default one. If you try to open a file in read mode and it doesn't exist, Python will raise file not found error. A means append. It opens the file for writing, but unlike write mode, it won't delete what is already there. It will start writing at the end of the file. If the file doesn't exist, it creates one. W stands for write. This mode also creates a new file if one doesn't exist, but it completely overrides the file if it already exists. X stands for create. So this one is useful when you want to make sure you are not overwriting anything. It will create the file but throw an error if it already exists. Now in addition to these, you can specify whether the file is opened in text and binary mode. T is for text mode, which is the default, and it means Python will read and write human readable strings, especially encoded in UTF-8. B is a binary mode, which is used when working with non-text files such as the executables, audio and image files. So when you combine these, you might use RB for reading a binary file or WT for writing text explicitly, though the text is default. Once a file is opened, you can read its contents using several built-in functions. Like read reads a specific number of characters from the current position in the file. If you do not pass any argument, it reads the entire file in one go. Read line method reads a single line from the file, that is everything from the current position up to the next new line character, that is \n. It is useful when you want to process file line by line. Read lines method read all the remaining lines from the file and returns them as a list, where each element represents one line of text including the new line character at the end. These methods make file reading very flexible. You can read just what you need, whether a few characters, a single line or entire file. When we read data from a file, Python keeps the track of where we are inside that file using something called a file pointer. Each time we read or write, this pointer moves forward automatically. But sometimes we might want to move back and forth in the file. For example, maybe to reread something or skip certain paths. That's exactly where random access and seek function comes into play. So the syntax is simple, f.seek, and you pass offset and then second argument is from. Here offset is how many bytes you want to move and from tells Python where to start counting from. There are three possible values for from. 0 means start counting from the beginning of the file. So f.seek 0,0 moves the pointer right back to the start. 1 means start counting from the current position. You can use positive or negative offsets here to move forward or backward. 2 means start counting from the end of the file. This is often used when you want to append data or inspect the end of the large files. The ability to reposition the file pointer gives us precise control over the file access, especially when dealing with binary files or when reading structured data in chunks. You can check the pointer's position using tell function. So seek works best with binaries or structured data where byte level control matters. In text mode, seek only works reliably with positions returned by tell because of text encoding. Up till now, we have been working with text files where Python reads and writes human readable strings like word, numbers in plain text form. But what if we want to work with raw binary data? For example, when saving images, videos or serialized numeric data. For that, Python provides a binary file handling mode such as WB for writing, RB for reading and AB for appending binary data. Let's look at an example. Here we open a file called file.bin using WB, which means write binary. Next we define a list of numbers that are 5, 10, 15, 20, 25. Now to write numeric data directly to a binary file, we just can't use write function on the list itself because write expects a sequence of bytes, not integers. So we use the built-in byte array function to convert our list of integers into a sequence of byte values. Each number in the list becomes a single byte. For example, 5 becomes that pattern ending with 101. After that, write method stores these bytes into the file exactly as they are, no encoding, no formatting, just pure binary data. Finally, we close the file to ensure all data is saved properly. The resulting file.bin now contains 5 bytes of data, 1 byte for each number in the array. So to summarize, writing to a binary file involves opening a file in binary mode, converting your data to a sequence of bytes, and using write to store it. This approach ensures that your data is preserved exactly as it is without any encoding or formatting changes. In Python, we can not only store text or byte, we can also store entire Python objects like dictionaries, lists, or even class instances. This process is known as object serialization, or in Python terms, pickeling. Here's how it works. We start by importing the pickel module. When we define a dictionary called data, which contains keys, values, or even a list, in other words, complex data structure in Python. To save this object to a file, we open the file in binary write mode, WB, and call the function pickel.dump and pass data_nf. This function converts our Python object into a sequence of bytes, a serialized stream, and stores it inside the file. When we want to bring the object back, we open the same file in binary read mode, RB, and call pickel.load. This function deserializes the byte stream and reconstructs the same Python object in memory. The result is we can pick up where we are left off with the same data structure without needing to parse or re-enter it manually. In this example, we are learning how to read data from a text file and transform it into a useful numeric values. We begin by opening the file f1.text in read mode. The function read loads the entire content as a string. Suppose the file contains text 45,67. Using the split comma method, we divide the string into parts where there is a comma, giving us a list of strings like 45 and 67 as entries. But notice these are still strings, not numbers. So we use a list comprehension to convert each element from a string to an integer. Now our list becomes a regular integer list with 46 and 67 element entries. Finally, we unpack the two lists into a separate variables x and y. This technique is useful when you know exactly how many values you expect to extract from the file. The output confirms the transformation from raw text to split strings to integers and finally to individual variables. So this is a common approach when dealing with comma separated data such as CSV files. So this simple example demonstrates Python's power in transforming the text file to structured list and to typed numeric values. You will use this same pattern often when dealing with text-based data files, logs, or CSV files. We have surveyed Python's core built-in object types that you will use every day, like numbers, strings, list, dictionaries, tuples, files, and sets. Each type has a clear use case, performance characteristics, and some common pitfalls. So in Python, sets are a collection of unique and unordered elements. Unlike lists or tuples, sets do not allow duplicate values and do not maintain order, which means there is no concept of indexing. Let's take two sets A and B with values like as shown here. Using the vertical bar symbol, we can perform union, combining all unique elements from both the sets. The result is 1, 2, 3, 4, 5, 6. Ampersand sign performs intersection, that is the elements common to both the sets. Minus operator gives a difference, that is elements present in A but not in B. The caret symbol represents the symmetric difference, that is elements that are in either A or B but not in both. So we get 1, 2, 5 and 6. Notice how each operation returns a new set because sets themselves are mutable, but these expressions don't change the original. Finally, if we want a version that cannot be changed at all, you can use frozenset type. So frozenset are immutable and hashable, which means they can even be used as keys in a dictionary. Sets are especially useful for tasks like removing duplicates, performing fast lookups. So, sets and frozen sets are Python's way of efficiently manage the unique and unordered data. They form the foundation for performing mathematical operations like we have seen union, intersection, and difference, all with simple and intuitive symbols.